Hello, Math 178 students. So, this is going to be our first online lecture. Now, I want to address a couple things. I know that the printed packets are a little blurry in my camera here. It's just because I don't have a very expensive camera, so it's semi-readable. But because I'm posting the packets into Canvas, I think that's okay. You should, even if you're not printing them out yourself anymore, at least have it downloaded and open in another window. So if you're not sure what something says on my packet here in the video, you can at least look at that. If you are printing them, great. You have those words in front of you as you are hopefully taking notes. You should all be taking notes. But we are into Chapter 3. This is the first section of Chapter 3. It's 3.1. It's all about first derivatives and finding maximum and minimum values and sketching graphs. So we have two things to talk about in this section. The first is the first derivative test. First derivative test. And the second is graph sketching. Now, the first derivative test does require some setup. And talking about graphing, the next bullet point here, it says that it involves calculus to find the most important points of a curve. So in pre-calculus, you would have looked at graphing with your intercepts, maybe some asymptotes, maybe some key points that you plug in to get the shape of the graph. But in calculus now, we can use the derivatives to find the most important. Now, along with first derivative test, we're going to be talking about optimization in a later section. But optimization just refers to finding the largest or the smallest values of a function. So we're going to be doing this a lot, like maximizing profit or minimizing risk if you have a model for risk. Again, though, we'll come back to that in a later section. We're going to focus primarily on graphing here in 3.1. So the derivative of a function we know gives its slope of the tangent, and so therefore we can use that test to determine the intervals where our function is increasing or decreasing. So our test for increasing and decreasing functions, if f is both continuous and differentiable on some interval I, we can say number one, if f prime of x is greater than 0, then f of x is increasing. So fairly straightforward. And number two, if f prime of x is less than 0, then f of x is decreasing. And so this is a really nice, easy way to test for increasing and decreasing. I have two graphs here that we can look at. So we have an increasing function, and I know that this is exceptionally blurry, but this is saying that f prime is greater than 0, because let's say we pick this point and we draw this tangent. The slope of this tangent, since it's rising to the right, is positive. So I'll rewrite it's f prime is greater than 0. Our derivative is positive. Over here, if we were to pick this point and draw this tangent line, this slope falling to the right is negative, or f prime is less than 0. So these are really easy things to do. We've been taking derivatives a lot lately. And now we can think of increasing and decreasing as rising and or falling as we move left to right. And that all comes from our derivative. So it allows us to use that derivative instead of guessing the old pre-calculus way. So the next thing we need to define then is relative extrema. Now, a relative extrema is also referred to as the relative maxes and minimums, or mins, because I'm lazy. So relative extrema, relative max, or relative min. So we're going to let f be a function defined at some value c. That's what that is. That's a C. So number 1, f of C is a relative max of f of x if there is an interval a to b such that f of c is greater than or equal to f of x for all x in that interval a to b. So what we're saying here is that the value f of c is bigger or tied for the biggest for all of our function values on that interval. And this interval can be as big or as small as we like. It can be as small as 2 points, it can be as big as infinite points, and that could change. And second, f of c is a relative min of f of x if on that interval a to b f of c is less than or equal to f of x for all x in AB. So relative max versus relative min. You're a max if you're bigger than everything else, and you're a minimum if you're smaller than everything else, or tied for the smallest. Right? That's why we have the greater than or equal to and less than or equal to. We can be tied for smallest and largest. So a little note here says relative extreme points occur in 2 different ways, either where the slope is 0, where the tangent line is horizontal, and where the slope is undefined. So at those corners, at those sharp points. So on the next page here, we have a couple examples. So we can see, oops, on this first one, all of these x coordinates are called critical numbers. So this point here is a relative max. So relative max. And that's because I can construct an interval where this is bigger than everything else, or tied. So we can make it small. We could say this interval here on the x-axis, from there to there. Or if we come across, we know that this is the last place that it's tied. So if I make the interval here, I can put it here again, or I could put it here. It really doesn't matter. But as long as you can construct one of these intervals, you have a relative max. Same thing with the relative min. Because this point is going to be smaller than everything, again, I can construct an interval like this. It's certainly smaller than everything in between those green dashes. So relative max versus relative min. If we think of that as 0 slopes, we have horizontal tangent here and horizontal tangent here. And if we think of maxes and mins as corners or sharp points, this is certainly still a max, this is still a min. You can still construct those intervals for this point and this point respectively. And again, at thinking of our slopes are undefined here because we don't have 0 slopes. As we talked about, we can construct a bunch of different tangents here. So that's kind of the geometric interpretation of our maxes and mins. So let's go ahead and define critical numbers. So this is our definition of a critical number. And we're going to let f be defined at C if f prime of c equals 0, or f prime of c is undefined, then c is a critical number. So our critical numbers are exactly where our derivative is 0, where we have horizontal tangents, or where our derivative is undefined, where we have sharp points or vertical tangents. So you can make a good note of this statement here. Relative extreme values occur only at our critical numbers. So if we want to find them, we're going to take our derivative, set it equal to 0, or look where it's undefined. But we do want to note that not every critical number produces a relative extreme value. That's what this line says here. So while all of our extremes occur at critical numbers, not every critical number is an extreme. It's not a two-way street. So I have a little graph here, example-wise, to highlight this. So we can think of maxes and mins. So this one, we have 0 slope, a horizontal tangent. So this would be a maximum because I can construct an interval like this, so because it's bigger. This down here would be a minimum. Up here, we would have another max. Down here, we would have a min. Here we have a max. Here we have a min. And this point and this point are special in that these are neither. So our slopes are still 0 right here, but because everything to the left of this point is smaller and everything to the right of this point is bigger, you can't construct an interval where it's bigger than everything or where it's smaller than everything. So we say it's neither a max nor a min. And over here, we have an undefined slope because it has a vertical tangent at this point. It goes straight up and down. But again, everything to the left is smaller, everything to the right is bigger. So it's neither. Now, this is a good place to talk about. We have 8 critical numbers, and all of these are relative extrema. So they're relative to the interval that you construct. But at some point we need to distinguish the maximum and the minimum of the entire function. So we look at something like C4 right here, and we look at C9. Let's call this one C9 down here, since I don't have it. Pretend that that's a straight line. They're supposed to be equal. So these are tied for bigger than everything else. So C4 and our added C9 would be called the absolute extrema, or in this case, absolute maximum. Because they are bigger than everything. The entire function, every other point, is their y values are smaller than these two y values, which are equal. So this is how we distinguish. We have relative extrema and we have absolute extrema. Absolute extrema are exactly what are implied. They're absolutely the largest things. And you've probably guessed we have absolute maximums. That means we also have absolute minimums. So our absolute minimums are the smallest things. So we look on the y values, and C5 is the absolute minimum. So every single absolute extrema, whether it's an absolute max or an absolute min, starts as a relative extrema. And you distinguish it based on the y values. So we have three classifications that we can have. We can have a maximum, we can have a minimum, we can have neither, and that's all relative extrema. And then a sub-classification. In your maximums and minimums, all the choices, you have some absolute maximums and you have some absolute minimums. Now you can be tied like we do here and have two. And here we only have one absolute minimum. But there's always a finite number of absolute extrema, except in very specific cases. And we'll be seeing examples of that in this chapter. So if we go on to the next page here, this is just highlighting what we were just talking about. So if you want to see it in a little bit more detail worded out, this is exactly what I just said. All of these are relative extrema, and only some of them can be absolute maxes or absolute mins because they are smaller in this case or bigger in this case than everything else. So we have what this section is all about, the first derivative test for relative extrema. So our first derivative test, we need a couple things. So first we need f to be continuous on an interval a to b in which c is the only critical number. So if c is differentiable, or if f is differentiable on the interval except at c, it could not be differentiable, right? Remember our extrema can be where the derivative is undefined. Then f of c can be classified as a relative minimum, a relative maximum, or neither as follows. So we're not quite to absolute extrema yet. This is just for classifying relative extrema algebraically using our derivative. So 1, if f prime of c, or if f prime of x is less than 0, on the left of f prime of c, and f prime of x is greater than 0 on the right, of f prime of c, then f of c is a minimum. So we have derivatives that are negative, and then we have our critical number, and then we have derivatives that are positive. So derivatives that are negative go down, we have our critical number, and then derivatives to the right are positive. So you can see it makes this kind of U shape. Now it doesn't necessarily need to be like this because it could do this and be a straight with a sharp corner here because we can be undefined. But this is the idea, is that we go down and then we go up. So we decrease then increase, which means that somewhere we hit a minimum or we start increasing again. So you can think of this little picture to figure out whether or not you have minimums. For maximums, if f prime of x is greater than 0 on the left, of f prime of c, and f prime of x is less than 0 on the right, of f prime of c, then f of c is a max. Again, we go positive slopes to negative slopes. So we are increasing up to a point, that's our critical number, and then we decrease after that. So we go up and then down, the opposite of what we did in number 1. And the third and final choice, if f prime of x does not change signs, at f prime of c, then f of c is not an extrema. So this is when things to the left are smaller and things to the right are bigger. So you can increase up to your critical number and then keep increasing. So we go positive, positive. Or we can decrease down to our critical number and then keep decreasing. Negative, negative. So these are the three options. This is what we want to be thinking about when we're testing for relative extrema. Do we go from negative to positive? Do we go from positive to negative? Or do we stay with the same sign? Positive, positive, negative, negative. And once you get a few problems under your belt and you get some practice, this will be a lot easier to identify. It's exceptionally easy when you have the graph because you can be looking for these types of shapes. So, flipping the page now, we have some guidelines for finding intervals on which a function is increasing or decreasing, and specifically finding those relative extrema. So, we have 7 things. A lot of these happen fast. The first is to determine the domain. Of the function. Right, we don't want to be looking at potential critical values that aren't actually in the domain. Then, take the derivative. Once we have the derivative, we set f prime of x equal to 0 and solve to find the critical numbers. Also, we need to look at and identify any places where f prime of x is undefined. Because those are also critical numbers. Then we're going to test the sign to the left and right of f prime of x at the critical numbers. So we need to see if it's positive or negative on the left and right of every single critical number. And then we can use the test for relative extrema. This is the first derivative test. To classify the extrema. And then if you want the relative extreme values, we plug the critical numbers into f of x, the original function, to get the extreme values. So this is usually where students make errors. When you're asked for the extreme values, you have to plug in your critical numbers once you've classified them to get those values. If you want the extreme points, you need to give your answer as an ordered pair. If they just ask you for the critical number or the x value of your extreme values, that is just your criticals once you've classified them. So I think I said there are 7 steps, there's only 6. But you got to do all of these things. You don't want to be testing outside your domain, so you have to make sure you're in the right domain. At this point, like we said a couple weeks ago, we should be taking the derivative on 98% of every question we'll see. We set our derivative equal to 0 and solve. That gives us the critical numbers. Once we have the critical numbers, we need to test them. So we can look to the left and the right to see if we're increasing or decreasing. And then use the first derivative test. Now these two things typically happen at the same time. Once we've classified our extrema, we can plug the critical numbers in to get our extreme values, which are the y values. So let's test this out and then use the information to graph. So we're going to find the open intervals on which the function is increasing or decreasing. So our domain, it's polynomial. It's all real numbers. So I'll rewrite this here so you can see it. It's minus 3/2 x squared. So our derivative f prime of x will be 3x squared minus 3x. We're going to set this equal to 0. Factor of 3x, we have x minus 1 equals 0. And so x equals 0 and x equals 1 are the critical numbers. So then we set up a little table. And you can think of this as a number line. And we're going to split the number line at x equals 0 and at x equals 1. And so we need to pick x values to plug in to test. So to the left of 0, 0. To the left of 0, we're just going to pick -1 because it's easy. So f prime of -1, since we have it factored here, let's go ahead and use the factored version. So f prime of -1 is -3 times -1 minus 1. And we don't care what this number is, we only care about its sign. So negative times a negative will make this positive. So f prime of -1 is positive. In between 0 and 1, we're going to test 1/2. So f prime of 1/2, this is going to be 3/2 times 1/2 minus 1. And 1/2 minus 1 is going to be -1/2, so positive times a negative is going to make this f prime of 1/2 negative. And over here we're going to test f prime of 2. So that's the next biggest one to the right of 1. So this is going to be 6 times 2 minus 1, which means that f prime of 2 is positive. So I like to draw little arrows here. I'm increasing, then I'm decreasing, then I'm increasing. And this is literally giving me that picture that we talked about in the last page. We are increasing to decreasing, so we have a maximum up at the top here. We have decreasing to increasing, so we have a minimum. So we're going to use this whole space for graphing in a second, but we can write our relative max is at 0, and the relative min is at 1. So now, if we go back to what a was, find the open intervals on which this function was increasing or decreasing. We're increasing here to the left of 0. So increasing to the left of 0 means -infinity all the way up to 0, not inclusive. And then union, we're increasing over here, which is 1 up to infinity. And our decreasing intervals then must be 0 to 1. So this would be our answer to part A. These are our intervals. Remember the union symbol? If you should have seen it, but just a review here. The union symbol is how we add up sets. So we're saying this and this. So negative infinity to 0, union 1 to infinity, decreasing from 0 to 1. We have our relative max at 0. We have our relative min at 1. So we need our f of 0, which is going to be 0, and our f of 1, which is going to be negative 1/2. So this gives us our points. So now in part C, we can graph. Now this is sketching, more or less, before we get to the big graphing section in a couple sections. So I'm going to give myself some axes, and I'm going to scale by 1s. This is negative 2, and this is positive 2. This is negative 2. This is positive 2. So we have 0, 0 is a maximum. We have 1, negative 1/2 is a minimum. Now because this isn't a linear function, you can take this general shape, which is why I like to draw these arrows, and we need to recreate this shape according to these points. So we need to increase up to our 0, 0. We need to decrease down to here, and then we need to increase again back up through 0, or after this 0, so it goes up like this. And then we label our points: 0, 0, 1, negative 1/2. And we can call this f. Now this isn't the best graph of f. It's by no means perfect, but we're building slowly in 3.1 and 3.2 to a full perfect, what we call calculus quality graph. But this is a good sketch. It tells us the max and the min. We have the general shape. Your shape comes from these arrows. You know you need to go up, down, up, and because it's nonlinear, we don't want to make straight lines. Because if they were straight lines, then everything in the function should be linear. But it's not. It's cubic, so we have this shape. Okay? So we flip the page here to the next problem. It's the same thing. We're finding the open intervals on which this function is increasing or decreasing. You can't see that though. There it is. And I'll rewrite the function so it's a little bit more visible. So this is x squared minus 4 to the 2/3. So first things first, we need to take the derivative. So f prime of x, using a chain rule, it's going to be 2/3 times x squared minus 4 to the negative 1/3, and then times 2x. So we need to set this equal to 0. So I'm going to write this as a fraction. This is 2/3 times 2x over x squared minus 4 to the 1/3. And this has to equal 0. So we have 4x over 3 times x squared minus 4 to the 1/3 has to equal 0. And so we're looking for critical numbers. Remember, critical numbers are where our function, our derivative as a function equals 0 or where it's undefined. So we know as a fraction, This will only equal 0 when the numerator equals 0. So this equals 0 at x equals 0. And then its critical numbers, where it's undefined, are where the denominator equals 0. So that would be a positive and negative 2. So that gives us our values to test. These are our critical numbers. And again, because x squared minus 4 equals 0 gives the undefined points. So, part B, we're finding the maximum and minimum function values. So we're going to set up our first derivative test. And we're going to split 3 places, at negative 2, at 0, and at 2. So we have 1, 2, 3, 4 things to test. We need to the left of negative 2. So we need to test f prime of, I'm going to do negative 3. We need in between negative 2 and 0. I'm going to choose f prime of negative 1. We need in between 0 and 2, f prime of 1. And to the right of 2, f prime of 3. So these are going into our original function, or not our original, into our derivative. So you can either use the simplified or the unsimplified. Now remember, we only care about the sign. So f prime of negative 3 is negative 12. I'm going to use the simplified version here. Over 3 times 9 minus 4 to the 1/3. So this bottom, 9 minus 4 is positive, so this is going to stay positive. Negative over positive is negative, that's less than 0. For negative 1, we're going to have negative 4 over 3 times negative 1 squared is 1 minus 4 to the 1/3. So this is going to be a negative 3, so we'll have a negative over a negative, which is going to make this positive. Then for f prime of 1, we'll have positive 4 over 3 times 1 minus 4 to the 1/3. So now we're going to have positive over negative, so that's going to make this negative. And then f prime of 3 will be 12 over 3 times 9 minus 4 to the 1/3, and we'll have positive over positive, which is positive. So if we take these signs into our little first derivative chart here, we are negative to the left, down, and then we're positive, and then negative, and then positive again. So that means we have a relative max at 0, and we have a relative min at both negative 2 and 2. So we need the function values as well. So now we need f of 0. F of 0 is, I'm looking at f prime. F of 0, plugging that into there, that'll give us negative 4 to the 2/3, which is the cube root of 16. And then we need f of negative 2. Well, negative 2 plugged into here is 4, minus 4 is 0, and f of 2 is 0. So this gives us 3 points. We have negative 2 comma 0. We have 0 comma cube root of 16. And we have 2 comma 0. And we have the general shape. So Now we can sketch our graph. So I'm just going to go by ones. 3, 1, 2, 3, 4, 4, 1, 2, 3. So plotting our points that we know, negative 2, 0, 2, 0, and then we have the cube root of 16, which is less than the cube root of 27, which would be 3, but more than the cube root of 2 cubed, so somewhere in between. It's closer to 3. I'm going to estimate it about right here. Now, we know this function is not linear, which means it does something interesting. Now, as it turns out, if we know, based on our first derivative test, that we have to be positive up to 0, negative down to 2, and we know it's nonlinear, then this has to curve in like this, and this has to curve down like this. And then it goes, we need to have negative slopes, but that means we need to decrease into negative 2. So we can't come from the negatives because this would be increasing. So we have to decrease down like this. And this would go off something like that. And then same thing over here. We have to increase from 2, so it would do something like this. And all that's left is to label our points. 2, 0, 0 cube root of 16, negative 2, 0. And we'll label this f of x. And I said as it turns out. As it turns out, these two pieces are linear for a couple of reasons that we'll talk about in future sections. But you want to be as precise as possible. Now, in this section, as I said in the last example, we're not headed for extreme precision. So if you had a curve, as long as you were increasing, I would count that. As long as you were decreasing here, if you made it curved, I would count that. That would be fine. As long as you have the right shape. We need to be decreasing down to negative 2. We need to be increasing to the right of 2. So as long as you have the general shape in this section, you'll be fine. So that was a fun little example. So this is kind of guiding you through the steps. In the next problem now, we are no longer guiding. We're just being told graph. So we have to know what to do. And that means following all of the steps that we just did. So the first thing we should be doing, taking the derivative. So that'll be 6x squared minus 6x minus 36. And then we need to set the derivative equal to 0. So that's 6x squared minus 6x minus 36 equals 0. Just pulling that down here. You can divide by 6. X squared minus x minus 6 equals 0. And then we're just trying to factor here. So what multiplies to negative 6 adds to negative 1? That would be negative 3 and positive 2. That should equal 0. So we have x equals 3 and x equals negative 2. And then you should always go back to your derivative, which is here as well, and ask yourself, is it undefined anywhere? And since this is a polynomial, the answer is no. So now we have our two values. We can set up our little first derivative test number line. And we're going to split at negative 2 and at 3. And so we need to test some values. To the left of negative 2, keep it easy on yourself, f prime of negative 3. In between, again, keep it as simple as possible, f prime of 0. And to the right of x equals 3, f prime of 4. You can pick any number you want, but you want to try and limit how much work you have to do. And again, we're not concerned with what the values of these are going to be, we're concerned with the sign. So we don't need to solve these all the way through. But this is going to be 6 times negative 3 squared minus 6 times negative 3 minus 36. So this is 6 times 9 plus 18 minus 36. 6 times 9 is definitely bigger than 36, so we know that this is going to be positive. And I don't need to know what the exact number is, just know that it's positive. F prime of 0 is negative 36, that's negative. F prime of 4, now we plugged the negative 3 in this way. For f prime 4, I want to show you that you can use your factored version, and it might make it easier. So this is going to be 4 minus 3 times 4 plus 2. Well, this is positive and this is positive. So this whole thing is positive. So we have positive, increasing. We have negative, decreasing. And then we have positive again, increasing. So that means that we have a relative max at x equals negative 2. And we have a relative min at x equals 3. So now all that's left is to find the values there. So I'm running out of space, so I'm going to come up here and do these little calculations. So for the relative max at x equals negative 2, I need f of negative 2. And that's just plugging negative 2 back into our function. And that comes out to be 58. And f of positive 3, plugging 3 back into our original function, that ends up being negative 67. So we have negative 2 comma 58. We have 3 comma negative 67. And then the other easy point that we should probably always try if we can is 0. 0 plugged into our original function will just be 0 comma 14. So this gives us some good points to plot. So we have 0, 14. This is going up to 25. I'll rewrite that here. 50 and 75. So it's going by 25s. Each little tick mark is 5s. The x-axes are going by 1s. Negative 2, negative 4, negative 6. And these, again, are going by 25s, negative 25, negative 50, negative 75. So 5, 10, 15, 14 is about right here-ish. We'll just put it right there. Then we have 3, negative 67. So that's going to be in between 65 and 70. If this is 75, the next tick mark is 70, backwards 65. So negative 3 in between those two, about right there. Make that point nice and big. And then negative 2 up to 58. So 50, 55, 60, it's going to be about right here. And then we're just looking at our shape. So we should be increasing into negative 2. So it should be going up into negative 2. Again, it's not a linear, so we know that it's a curve. Then we need to decrease down to x equals 3. So we decrease all the way down, go through this point as best as we can, down into that point, and then we increase out from x equals 3, back up like this and like this. And then the last thing we do is label the points, 0, 14, 3 comma negative 67, and negative 2 comma 58. And we have a pretty good graph of f of x, labeling that. It's not perfect, but again, we're not trying for perfection here. We're building slowly into calculus quality graphs, but this is the first step. So now that you've seen these, you should practice. The next sheet is true practice, since you have them. I want you to do these on your own. These are good things to schedule some office hours with myself or O'Neill. So work on these, and if you want to see solutions, talk to one of us and we can help you through it. And this is the end of 3.1.